Alright, last little bit of acids and bases that we're going to talk about in Chemistry 1 includes the method of titration, okay? Specifically, this is going to be an acid-base titration. There are several methods of titration that we can discuss, but obviously we're going to talk about the acid-base method since we're talking about acids and bases in this chapter. Now, let's talk a little bit about what is a titration. Well, a titration is an analytical method used to determine the concentration of an unknown solution using a known or standard solution. So if we know the concentration of one solution, we're going to perform a test that will tell us the concentration of the unknown solution. This is one of your upcoming labs. Now, an acid-base titration depends on the method known as neutralization. Okay, neutralization. We've already talked about neutralization reactions, correct? Neutralization reaction is when we take an acid and a base and we yield a certain product. And hopefully you remember that an acid plus a base is going to yield a salt and water. Remember? An acid and a base yield salt and water. Okay? Now, if we have a strong acid and a strong base, we end up with a neutral salt. Okay? We end up with a neutral salt. Salts can be acidic or basic or even neutral like we have here. If you use a weak acid plus a strong base, you're going to end up with a basic salt. And you probably can guess that if you use a strong acid with a weak base, you're going to end up with an acidic salt. Now, a neutralization reaction does not mean that pH equals 7. Neutralization does not mean that pH equals 7. It simply means that you have an equal number of H plus ions or hydronium ions and hydroxide ions in solution if we're dealing with a strong acid and base, which we do when we do a titration. Okay? Now, again, a titration is an analytical method used to determine the concentration of a known solution. Okay? Typically, when we're performing a titration reaction, we have a ring stand, a burette with a burette clamp, and a standard solution that we know the concentration of. Typically, what I like to do is I will give you a base as the standard solution. Okay, we use a burette. A burette measures how much liquid is delivered to the Erlenmeyer flask below. Now, this unknown solution, we know how much unknown solution we have. We just do not know the concentration of the unknown solution. So what we do is we add the standard solution in the burette and we distribute a certain amount of that standard solution into our unknown solution. Okay, so we know the concentration of our standard solution. We know the amount of standard solution we're using. We know the amount of unknown solution we have. But what we're trying to solve for is the unknown solution's concentration. Okay, so what we do when we're performing an acid-base titration is we have to reach the equivalence point or the end point. Okay, sometimes you'll see those referred to as kind of the same things, though they're a little bit different in definition. Okay, the equivalence point is the point at which the H3O ions or the hydrogen ions from the acid and the OH ions are equal. Okay, that's when they are equivalent. They are the same. We determine that based upon an indicator. Okay, and like we have here, you can see over in our solution, is it started out clear. We added some of the base to it, and it turned a slight pink. The indicator solution that we typically use is phenolphthalein. Phenolphthalein is good for a strong acid, strong base titration because it has a pH sensitivity range of around neutral. It turns pink when it gets slightly basic. And what you look for is you look for a slightly pale color. That means that the number of acid ions equals the number of base ions. So the H3O plus equals the number of OH. Okay, so it's around pH 7. We're looking for a pale pink. We can also do that, or we can also perform a pH by measuring a titration by measuring the pH and plotting that data, which is what we have here. It's an experiment we do in chemistry too. What we do is instead of looking at an indicator every so often or every at certain intervals in our volume addition of the base, we'll measure that volume addition and or not measure the volume addition. We will measure the pH and plot our pH versus our um, volume of standard solution, which will give us a nice graph. What we're looking for is a dramatic change in pH. Typically, when you see the equivalence point, this is when it should turn slight pink. Notice that if you add just a little bit more, the pH is going to jump dramatically. Okay, that's why you have to be careful in a pH in a titration lab, because if you add just a drop or two too much, you may end up with the pH being dramatically affected. Okay, now you can solve pH problems for the unknown. Rather, you can solve for the unknown using stoichiometry. It's probably the better method to do it, but I like to simplify it just a little bit for y'all because life's too complicated without having to determine the concentration of an unknown solution using a complicated dimensional analysis problem-solving method. But I've kind of broken it down to a very simple way to uh, figure that out. And it's simply this formula, this last formula. We know that the moles of hydronium in a titration equal the moles of the hydroxide. So from that, we get a formula of MVN equals MVN. Okay, that's going to leave us with our moles canceling out and solving for one of them. All right, M is the molarity, V is the volume. You can either leave it in, you really should probably convert that to liters. That way all of our units are the same, though sometimes you can leave it in milliliters. It's best to convert it to liters. And N is the number of H ions in the acid or the number of OH ions in the base. What does that mean? Well, you look at the formula, look at the chemical formula. If it's HCl, then there's the N value for HCl is 1 because there's one hydrogen. If you're looking at sulfuric acid, H2SO4, well, the N value is 2 because there are 2 hydrogens that you're going to lose in the reaction. Okay, or 2 hydrogens that are going to be transferred, rather, in the reaction. If you're looking at hydroxide, it's the number of OH in the base, the number of hydroxides in the base. So if we're looking at sodium hydroxide, NaOH, we only have one hydroxide present, so N would be 1. But if we're looking at something like, for example, calcium hydroxide, Ca, open parentheses, OH, close parentheses, 2, we have 2 hydroxides in calcium hydroxide. Okay, so our N value would be 2. So let's take a second and look at an example problem. 42.5 milliliters of 1.3 molar potassium hydroxide are required to neutralize 50 milliliters of sulfuric acid. Find the molarity of sulfuric acid. So sulfuric acid is our unknown. So let's look at our acid side first. The M is what we're trying to calculate. The V, the volume of the acid, is 50 milliliters. Now remember, we know that. That's in the bottom Erlenmeyer flask. Okay? And the N value of H2SO4 should be 2. Where do I get that from? I have to look at the formula of H2SO4 to get the N value. Okay? If it's 2 hydrogens, then N has to be 2. Okay, let's look at our base, our hydroxide. We know the molarity is 1.3 molar. We know the volume that was required from the burette was 42.5. This measurement is always taken from a burette. Okay, 42.5. And our N value of KOH should be, how many hydroxides do I have? I've got 1, so the N value should be 1. All right. Now I simply plug this into my MVN equals MVN, where I use the pound sign for numbers, and I know sometimes that confuses y'all. The acid side we're going to use to the left, the base side is going to be on the right. So the molarity times 50 times 2 is equal to the molarity of the base times the volume of the base times 1, because remember, we get that information from over here. Acid on the left, base on the right. And once we put it in our calculator and solve for M, we should end up with a molarity of 0.55 molar H2SO4. Again, that's just a nice, easy way of calculating the concentration of the acid. Okay? And that wraps up the titration method. If you need to watch this video multiple times, please feel free to do